So good afternoon, everyone. It's my pleasure to introduce you to Francesco Bonaldi, associate professor at Maitre Complément at the University of Montpellier. Perpignan. Perpignan, sorry. I had so much Montpellier in my head. Sorry. You'll see why. So Francesco did, he's originally from Rome. He did his bachelor and master in mathematical engineering in Tor Vergata in Rome. Then he did his PhD in the University of Montpellier with applied mathematics. And he has postdoctoral experience in India, in Nice, in Montpellier itself, and in the MOX laboratory in Politecnico Milano. And since 2022, he's associate professor in applied mathematics at the University of Perpignan. So thank you. Well, he has worked on contact mechanics, porous media, discontinuous collecting, etc. And today's talk, I think, will be more related to contact mechanics. So thank you, Francesco, for being here, and all yours.
Well, thank you so much for this introduction, and maybe sit down. So it's a really honor to be here and to present some of the advancement some recent advancement that we made with my colleague in Perpignan. So Mikaël Barboteu and Serge Dumont, my colleagues, I owe a lot to them. And there is also this intern student that collaborated with us back in, I think it was 2023, for 5 months, and now she's doing a PhD in Montpellier, Christina Mahmoud. So the title is the hyperelastic model with the contact and viscosity, and the application involves the simulation of stents in arterial tissues. So there are 2 keywords in this title. Contact and let's say contact and tissue. So let's say first I will start by mentioning a few facts about software biological tissues. So this is my first slide. So soft tissues can be thought of hyperelastic bodies, and the macroscopic properties, mechanical properties, are actually determined by the influence of collagen and elastin proteins, and can undergo very large strain, so up to 15% without damage. So you see in this picture, this is kind of a brain, and this is a kind of a numerical model, and this is the plot of the stress strain curve. So the constitutive law is typically hyper viscoelastic. So the viscoelastic behavior is quite important. And there's been a number of people working on that. I think especially Mikaël 𝗔𝗕𝗧𝗧, who is in Galway, in Ireland, and but also Chioleti and Rakotomanana have been working a lot on the modeling of soft tissues, soft biological tissues, and they employ the hyperviscoelastic constitutive law. So on the one side, on the one hand, we have soft tissues, and on the other hand, we have stents. What is a stent? A stent is a structure that has to be able to be squeezed. It has to be able to be inserted into an arterial in an arterial wall by a catheter. And once they are in place, they regain the original shape following the type of material they are made of. Okay? So in this talk, I will focus on hyperelastic stents, but you can also have a superelastic stents, which is the case for nitinol structure, nitinol stents. So in this case, you don't have to inflate the stents once it's in place, but it regains the original shape in a spontaneous way. Okay, this is the case, for instance, of shape memory alloys, and Ferdinando Auricchio and Robert Taylor, his supervisor, have been working a lot on this subject. And so as I just said, we have been working on that also. But in this talk, I will focus on hyperelastic models, and it will be the case for silicon stents or even stainless steel stents, if you think of them, of stainless steel stent as a hyperelastic bodies. This is a 3D example. This is just a schematic of a simulation of the deployment of a stent in an arterial wall. so you inflate and then the stent stays there. Okay, so this is the outline of my talk. So I started with the description of the model, the contact part, the constancy law, etc., etc. Then I will move on to the energy consistent discretization. Discretization, I will mainly focus on the time scheme here, because we look at we try to conserve energy over a time step. And also the space discretization part is also quite important. And for the contact part, we're going to use the active set method. Okay, if you heard, Barbara Barboteu has been working a lot on this kind of semi-smooth Newton method. It's a version of the semi-smooth Newton method. Okay, then I will show some benchmark test cases, and finally a real life example, a 2D example actually, which is the deployment of a stent in an arterial wall, in an arterial tissue, and then I will conclude. So this is how this is the outline of my presentation. So I start with the model. So okay, so we have a contact problem. We have two bodies that can undergo large frames. Okay, so body number 1 and body number 2. So first, I will mention that the problem is not symmetric. So in the sense that you have a master and you have a slave, or you have like a contactor and a target, so you cannot switch from one body to the other. So the things go like this. So in the deforming case, you take a point of the deforming contact surface and you project it orthogonally onto the deforming contact surface of the let's say of the slave body, and this gives you the closest point projection. And once you do that, since you want to work on the initial configuration, what you do is you do the pre-image. You can show that the pre-image of this point here is actually what is called the proximal point projection, which is this one, is the pre-image of this point at this time, at time t, by this the deformation of body number 2. Okay, and once you do that, you can define the gap, the normal distance, which will intervene in the contact lows, which is defined like this. So nu is the normal to the contact surface of body number 2, and the contact velocities are defined in this way, which, I mean, this is not the time derivative of this distance. Okay, you have to carefully tailor the definition of the normal contact velocity and of the tangential one as well, because of material objectivity reasons or something like that. So this is even though the natural definition would be just the time derivative of this function, this is not the case here. Okay, so this is the normal contact velocity, and then you project this onto the tangent space of the tangent plane, let's say, of the deformed contact surface of body number 2, and so you have this this quantity that have been defined. Of course, this is not new. This is something that comes from works that date back to the beginning 2000s. Alain Tournier and his PhD student Gregor Pieszak have been working a lot on that, on these things. And for the contact law, so once we have this in mind, once we have settled this these quantities, the contact law is a single law. Okay, here, so we have the gap has to be positive. Then we have a compression here, because gamma nu is the stress, is normal stress, which body number 1 applies to body number 2. Okay, and then you have this complementarity conditions. That means if you have a gap, you don't have the normal stress, and if you have normal stress, the gap is no. Okay, and then we have the friction law is a Coulomb one. So the tangential velocity is parallel, is collinear, let's say, to the tangential stress. And this is a threshold law, and this is again a second complementarity condition that intervenes in the Coulomb's law. And we add to this model, we added the persistent condition, which is this one. Essentially, it means that the normal stress intervenes only when the contact is persistent. Okay, and this is important to ensure energy conservation even at the continuous level. And it was first introduced by Moreau in 1999 and by Todd Larson in his book in 2003. So it dates back to some years ago, quite a lot. So it's not actually new, but it's important to ensure energy conservation over a time step. Okay. So the strong formulation of the problem is this one. Okay, so we have two bodies, and the stress contains a viscous part and which is in this one, and an elastic part, which is this one. So the elastic part, of course, is the derivative with respect of the deformation gradient of the elastic energy density function, and WB is a viscous power which you derive with respect to the time derivative of F. And then you have the standard law, so momentum balance here, boundary conditions, initial conditions, etc., etc. Sorry. Then you have the contact law that I just showed you in the previous slides. You can prove that if you add the persistent condition, you can modify the contact law in this way. So you have the normal velocity that intervenes here, that intervenes in this complementarity condition. And concerning the Coulomb law, this is not modified. Okay, if you have a persistent condition, which is here, the contact law is modified. Starting from this contact law, you can modify, you can change it. You can prove that it changes like this. So if you have a gap, you have no contact normal stress, and if the gap is no, we have suitable compression stress, which is here. Okay, so this is on the contact boundary, and we have the Coulomb law on the same boundary. Okay, so this is the strong formulation. So the weak formulation is this one. So omega is given by omega 1 and omega 2, the union of omega 1 and omega 2. And then you introduce the suitable subbolus space, Hilbert subbolus space, let's say. And now the weak formulation is that, I mean, you have to find for each fixed, let's say, to simplify things, for a given time t, you find the displacement field and the stresses, the contact stresses, which lie in some suitable dual spaces of h1/2 on the contact boundary, such that we have the following principle of virtual work or virtual power, as you like. And the power of the contact stresses is highlighted here, and this is quite technical. Contains some suitable directional derivatives of the normal distance with respect to a suitable test field, and of the tangential distance, contact distance with respect to the velocity test field. Okay, it's quite technical. And so this V orthogonal 2 is the velocity test field associated with body number 2, evaluated at the proximal point that I showed in my first slide. Okay, now to discretize it, at first I will focus on the time scheme. So the time scheme is crucial here, because we are in a dynamic hyperelasticity, let's say, with a viscous term. But essentially, the key part is this one. So we use a midpoint scheme. Okay, a midpoint scheme. So the velocity at time I+1 is expressed in this way, and the problem amounts to finding the displacement field at time I+1, such that the following holds. So everything is taken at the midpoint, even the work of the contact stresses. The discrete counterpart of the elastic component of the Kirchhoff stress is discretized in this manner. So this is the first Kirchhoff stress. The first Kirchhoff stress is given by the matrix product the deformation gradient at the second pure stress is taken in at time I plus 1/2, but the second pure, the discrete counterpart of the second pure kick of stress is given by this expression here. The key thing is that you have to take you have to add this term here. If you keep just this term here, this would be just a standard midpoint rule. Okay, if you just consider the first term, which is here. But in order to conserve energy over a time step, you have to add this further term, and this was proved by 𝗔𝗕𝗧𝗧 in 2000 in a paper that was published on CIMNE. Okay, and this is very important to add to include this term, which is here. Here W is the energy density, the hyperelastic energy density function. Okay, and delta C is the variation of the right Cauchy-Green tensor over a time step. Here, just point out that the variational derivatives of the normal and tangential contact distances contains. I mean, the correct normal depends on time. So I stress this point by putting this index here. I mean, everything is taken at time I plus 1/2. So this is the discrete counterpart of this formula here, these two formulas here. Okay, so these are the contact stresses, which are also taken at time 1 plus I plus 1/2. Now, the key point, the main contribution of this paper is this one. So to discretize the contact condition, we introduce a suitable leapfrog normal distance in this way, and the discrete contact velocities are defined in this way here. And so we discretize the persistent frictional contact conditions in this way here. Of course, if the gap is positive, is strictly positive, we get no contact stresses. And otherwise, if the gap is no, we have to take into account the persistent contact condition in this way. So this is the discrete contact velocity, and this is the complementarity condition that I just showed you a few slides ago. And this is the frictional part. So this contains this is the Coulomb part, containing the frictional coefficient is mu here. I didn't say that before, but the frictional coefficient is mu, which is just here. Okay, this is how we discretize in time, but it's very important to have this time schema for the contact part. Otherwise, you don't have energy conservation without friction. Okay, it's very important. Also, I didn't mention concerning viscosity. It also we also take it the pure of stress, the viscous pure of stress at the midpoint at time I plus 1/2, which is here. I mean, the step here. The important part is more this one, but we also take the stress at time I plus 1/2. Okay, space-time discretization. So here we use the standard finite elements. Okay, so in the code we just take k equal to 1. Okay, here in the for the theory you can take any k, but in the code we just took k equal 1. And this is the fully discrete problem in time and in space, where still at the discrete level we had this split version of the stress at time 1 I plus 1/2, the elastic part and the viscous part with frictional contact conditions. And now I insist on the space discretization of persistent contact condition, which is this one. So you take a vertex of the on the contact boundary, okay, and so if the gap is positive, strictly positive, no contact, so no contact stresses, and if it's no, persistent contact conditions, okay, and along with that, we have discrete friction condition, which are the standard Coulomb one. I will mention that here you don't have to confuse. Here the gamma mu and gamma tau are sorry, gamma mu comma p is not a stress in the actual sense of this is it's more a force. Okay, it has to be thought of as a force and not as a stress, not as a density of forces. Okay, just to highlight this point. And then so once we do that, we can reformulate the contact condition in this way. So we have, for the persistent contact part, we introduce a complementarity function, which is this one. And for the frictional condition, we have this one. Okay, so you can prove that this set of conditions concerning persistent contact, which is here, can be reformulated as the roots of this function. Okay, of this function. Yes. As well as the frictional condition that are here. Okay, this frictional condition can be reformulated as in these terms here. And once you do that, you can apply a semi-smooth Newton method, or if you like, a Primal active set method, which is like a rewriting of essentially of the semi-smooth of a semi-smooth Newton method. The the Primal active set method was first introduced by Muller in 2003, and then considered by Barbara Warmwood and other co-authors some years later. So they laid the basis for this kind of methods. But here we do that for persistent contact and for friction as well. Okay, so once we do that, this is the Primal active set method. So what we do is at each time step we identify a set of active nodes. We identify a set of active nodes, which are the contact nodes, and a set of inactive nodes, which is the set of gap nodes. And if you consider the set of contact nodes, we can define a subset of the set of contact nodes, which contains the nodes that are sliding and the nodes that are sticking. Okay, it depends if the tangential stress overcomes the threshold for friction. Okay, which is this one. And so at each time step, you have to solve this nonlinear system. This stands for the principle of virtual war. And then you have the complementary functions that are just here. Okay. All right. So this is how things work. Now I go on to the numerical tests, numerical experiments. So first, I will present two benchmark examples. The first one is a viscoelastic ball in the framework of small strains, but large displacements. Okay, because we throw this ball against a foundation, a rigid foundation. This is the case of the small perturbation theory. So the gradient of fluid is quite small. The viscous power is expressed in this way. Is expressed by this is the Fourier law, and this is the standard linear elastic isotropic elastic energy. Okay, where it is the Young modulus and kappa is the Poisson's ratio. So this is what happens. I cannot zoom in and out, but this is over a time step, let's say, during impact, before, during, and after impact. So we want to check the energy conservation. Okay, without viscosity, this is what we obtain. So we compare this with a lot of schemes. Our scheme is here, so we have perfect energy conservation. This is the impact time, and we have a precise energy conservation even after the impact time. We compare with a lot of schemes, for instance, the equivalent mass matrix, which was proposed by Krebs, Laborde, and Ivrenat, and also with some other schemes, such that scheme with signorini and persistent conditioning. In all this case, we have some numerical dissipation of so the only case where we have perfect energy conservation is when we apply this active set method combined with including persistency conditions concerning contact. This without viscosity, and with viscosity we obtain this behavior, which is quite expected. I mean, because we want to have only physical dissipation. Okay, and this is the case here. So after impact, you see the influence of eta. So when you increase eta, of course, you have a larger dissipation. So the higher eta, the higher the energy dissipation. This is still with the set method with both persistence and viscosity conditions. Second example is a hyperviscoelastic ring that we throw against still against a foundation. In that case, this is a hyperelastic case. So we can use a 𝗔𝗕𝗦𝗧𝗧 law, which is an improvement of the Ogden law. Okay, the Ogden law is quite used for tissue, for soft tissues. So here we use a 𝗔𝗕𝗦𝗧𝗧𝗧 law, and so this II, let's say, are the invariant of the left to the right Cauchy tensor, the determinant of the trace, and the second invariant. And for the viscous part, we have the 𝗔𝗕𝗦𝗧𝗧 viscous power density, which is expressed again in an analogous way to the small perturbation case in terms of the time derivative of c, of the square of this tensor. And so we have the configuration is what happens before, after, and during impact is this. Okay. So it deforms a lot, actually, as one expects. And so this here we tested without viscosity, and still we have energy conservation with our scheme, which is the leapfrog with the persistent conditions. For instance, you can clearly see how we don't see the other two methods, but with respect to the equivalent mass matrix, you see the improvement in terms of energy conservation. Okay? Without viscosity, and with viscosity, of course, you have the physical dissipation that we expect. Here we just increase slightly the viscosity parameter, and of course, without viscosity, we have perfect energy conservation, even during impact, and otherwise we have some energy dissipation when we increase beta, which is quite natural. The last case is where we tested. So here we fix this is without viscosity, but we play with the friction coefficient, and you still see some dissipation when we increase the mu, which becomes higher and higher as you increase mu. So you have this behavior, which is quite expected, and that's all, I guess. Do one final test case with when we fix the friction coefficient here, and we play with the viscosity parameter. Here again, we see some dissipation when you increase eta, and you fix the friction coefficient here. Okay. Now I move to the last example, which involves two bodies. Okay. And is the deployment of a stent in an arterial tissue. This is just 2D. So the stress state is a plane stress state. It's not axisymmetric. It's just plane stress state. For the hyperelastic energy, we select the 𝗔𝗕𝗦𝗧𝗧𝗧 density, which is expressed like this. For the viscous part, again, the 𝗔𝗕𝗦𝗧𝗧𝗧 law. This is the data set, density, time step, etc. This is the initial configuration. The stent is made up by two plates. Plates not in the sense of not in the mechanical sense, but in the geometrical sense. Okay, two let's say rectangular pieces which are here, and so we impose a homogeneous delineate conditions on all this part of the boundary of the artery, and symmetrically on the other part. And what we do is we impose an orthogonal displacement to the inside the with the internal interface of the stent, which are here. So we we don't push, we impose a normal displacement, okay? And these are the values of the material parameters, and these are the values of the constants intervening in the active set method. Okay. Okay, what we do is the following. So this is, as I told you, is a hyperelastic stent. So we have to insert a balloon that we inflate, then we release the stent. So this, as you can see, there are large trains here. Okay, there are essentially two steps. Okay, this is the initial state, then the inflation state, and then at some point the final state is when the stent remains, sticks to the wall, to the arterial wall. There are three, let's say, two phases in this numerical tests. This is the end of the first phase, and this is the end of the second, on the second phase. I mean, it's when we remove the balloon, some sense. Okay, so these are the sort of meshes, and in terms of energy conservation, we have these properties. This is the total energy, and so without viscosity, you have this. Sorry, with viscosity, but without friction, we have this behavior here, which is quite expected. I mean, if you increase it, you have a larger energy dissipation. This is when we fix the viscosity parameter and we increase the frictional coefficient. And again, we have the this dissipation, which is increased as you increase the frictional coefficient, right? So this is the viscosity here is always equal to 1, and this is why the black curve here is not perfectly constant. It's not a horizontal curve. It's slightly it decreases slightly, and otherwise you have the energy dissipation is more consistent in the other. It's more remarkable in the other cases due to the presence of mu. All right, so to conclude what we did in this work, we presented a hyperviscoelastic frictional content model in persistent condition with an energy consistent time integration scheme based on a leapfrog procedure with weak point for persistent contact. The space discretization of contact is based on an active set method. As I showed you, we compared with several other schemes. If you had mathematics, penalization, and so on and so forth. And finally, I presented a real-life scenario, just in 2D for now, of the deployment of a stent in an arterial wall. There are several perspectives. We did something on superelasticity already, and something on the adhesion part. So we submitted a paper yesterday on this part. So we did a lot here. The next step is to extend the 3D case to have a fully complex stent artery scenario to simulate real life stent artery scenarios, and also possibly to study possible the decomposition method because 3D problems are going to be very expensive, and so the composition method go along HPC technique. So both these are good perspective, but I don't know if we will be able to tackle this part. I mean, it's going to take some time, I guess, and there's a lot of work to even to extend what we did in the 3D case. But okay. So okay, I think I finished. I'm finished here, and well, so thank you very much for your time. And this is the paper if you are interested. That's been published last year on the CIMNE. Thank you again.
Thank you, Francesco, for this very nice talk. We have time for questions.
Thank you for the talk. I have a couple of questions. Maybe I missed that, but I don't see how do you approximate the time derivative of the displacement itself, because you've written the discrete problem considering a continuous derivative of the displacement, right? Here, for instance.
This is in time.
Right. So you have u dot us plus one, I plus one.
Mhm.
So how do you discretize this u dot?
This is a standard midpoint scheme. I mean, it's
I mean, you still have to write that in terms of displacements, right?
yeah, in terms of the.
How do you do that? So here,
I'm not sure I understood the question. What you mean?
so you have the velocity there. You don't have the displacement itself.
No. I mean, this is given. You have to initialize, right? So it's at time zero. This is given. The quantity
Yes,
here
but
is given.
at time you want I plus one is not given. How do you obtain u dot I plus one?
I mean, okay. What I do, I express u dot at time I plus one in terms of u I plus one. So the unknown
Right.
is this one. Is this one at the time step.
That doesn't understand.
It's
Yes.
the unknown
Okay,
here.
okay, you have it there.
This is my unknown here. Okay. This is my unknown here.
Okay, but okay.
Because
I see that you have it
if you
there.
insert this expression here,
Yeah, okay.
you get
I see. You have a dot there. Yes. Okay.
yeah, maybe I cannot zoom, but
Is that unconditionally stable? Because this is a version of Neumann scheme essentially.
this is the midpoint scheme combined with the Gonzalez stent, so it's very good. Yeah,
Midpoint scheme with another one. Yeah.
exactly. So it conserves the energy very well. It's without contact, even without.
And the other question refers to the constitutive law that you have used for the viscous part. You have written the just the potential and it's just the viscosity multiplying the trace of it. So
the trace of
is it the whole right 𝗔𝗕𝗦𝗧𝗧 intensor is not the deviatory part only?
no, it's the
You
whole.
apply viscosity everywhere to all components of the stress.
Yeah, that's the time derivative of
Right, of the stress.
C dot to the power 2. So all the right 𝗔𝗕𝗦𝗧𝗧. Yeah, I don't think that's the deviatory part. No. It's the
I
whole.
mean, usually, one considers only the deviatory component of the stress to be related to with a viscosity to the strain. In this case, a measure of a strain, which is not really a strain, it's a right 𝗔𝗕𝗦𝗧𝗧 tensor. And then one uncouples the volumetric and the deviatory component.
Well, this is okay. As far as I saw, people do that in plasticity mode, right? I think more than and for as long as I saw through the paper that I came across. Yeah, I'm not expert maybe at this point, but
no, this is, I mean, that's acceptable as soon as you don't want to uncouple the volumetric and the deviatory part.
I don't know. This is just a test because we and just to test the energy conservation. So we just picked this law to see if things worked well in this case. Then of course you can play more. You can use more advanced law, but we decompose the deviatory part and the spherical part. But we start with this case. Yeah.
Thank you.
Questions?
Okay, thanks. Thanks for your talk. Now, I have questions regarding the numerical examples. I'm going to make maybe 2 or 3 and keep others for maybe later. Can you show the last example?
The stent.
The application, the stent. Now, you mentioned at some point that you used so this plane strain description, not axis symmetry.
Yeah, it's
Is that because that's what you coded, or for any? I mean, is there any fundamental reason for
no,
that?
just a first test case. So in the code, it's just plain stress.
Okay.
Yeah,
Okay,
just
understood.
of
Now,
course.
if this is plane stress, if this is plane strain, once you remove the balloon, the stent does not hold there, right? I mean, it brings it back into. I mean, because the stent is not working as a perforated tube without axis symmetry. You don't have hook stresses there, so one, I mean, when you remove the balloon, why doesn't the artery and the stent
collapse.
collapse, spring back into their original and before configuration?
Because we have full adhesion here. I didn't mention that, but this example includes full adhesion. Yeah. The adhesion we didn't in the paper we didn't put many details about that, but we also impose full adhesion, complete adhesion. So actually, this is a first ingredient that I didn't have time to talk about. Okay, so actually the law that we employ here is the Talon-Curnier law, which is another like layer of it's a further law. Okay, you have to impose that in some sense. I fully agree with what you said.
So adhesion changes the stiffness of the. And now regarding so one second question regarding the first example, the first benchmark test. Can you show the?
Yeah, with the ball.
Is the foundation rigid?
Yeah, rigid.
So what are these?
These are the contact forces. It's not. They're not displacements. These arrows here are just the contact forces, which are expressed in this way because otherwise you wouldn't be able to see them. They are compressional forces, but we plot with the opposite sign.
I didn't understand the figure. I thought those were like some sort of weird indentation into the.
No. This is not. This is a rigid foundation.
Okay, understood. Thank you.
I wanted to ask you, what if we had a self-contact species? Is this model is going to work as well as two objects?
You mean one body that undergoes self contact? No, it doesn't. This model doesn't contemplate. Doesn't include this feature. No. That would be a. I mean, this. Yeah, this is a condition that I think it's quite delicate. I never dealt with this, but I think that there is some problem with the determinant of F, right? Because if you have self contact, you have some problem with the determinant of the deformation gradient. So you have you almost have an auto intersection in some sense. So it's not trivial. I never dealt with that, with this kind of problems. But I think it's far from being trivial, because you have to impose something more. Otherwise, the condition of the admissibility of your deformation is violated, because the determinant of F must be positive. And if you have, I think there is some singularities. I mean, if you have auto contact, so it's I never thought about. I have to dive into this, but I never. So far, I never dealt with this kind of problems.
What is structure tissue engineering? Like
yeah, okay, I see what you mean. Yeah. But no, okay, we are not. This kind of model doesn't include this behavior. No.
Now, question regarding the second example, the
ring.
The ring.
Yeah.
Okay. So let me put it down like this. It would be so nice to see an animation of this. I'm asking because I'm trying to understand. So when the ring, at the end of the process, when the ring, so to the right of the picture, what's happening with this ring? Is it
bounces.
Rotating, or is it opening and closing?
It's rotating. It's also rotating. Yes. Yeah. You see that more remarkably when you have a friction, of course. When you don't have friction, for instance, if you throw this object vertically, you see it just bounces. But if you have friction, it rotates as well. If you throw it vertically, if you throw it with an angle of 45 degrees, like in this case, it's more difficult to distinguish, to separate the rotation.
It would be nice to have either an animation or at least showing, say, 4 points in the original circle, A, B, C, D, and then tracking them.
In time, what do you mean? In time or
in the picture.
The surface, as long as it deforms in order to understand whether it's just stretching or it's also.
Exactly. So you can go from this to
No,
this either by a, say, almost rigid rotation, okay, or by stretching and compressing.
I know what you mean. Yeah, I have maybe I have a simulation that we made with Paragroup. There is a movie of that, but I should.
No, I'm not.
Yeah. Okay. I don't want to live. I should do this right
I
now.
want to see it right now.
I could maybe later I can show you, but
maybe also a line plot of the center of mass, the trajectory of the center of mass, and then a line plot of another point in the. So if they intersect, you would see that there is rotation.
Exactly.
If they go parallel, you would
Exactly.
see that there is no rotation.
Exactly. So
yeah, maybe that's a good.
some way of distinguishing, let's say, rigid motion from deformation.
Exactly.
Okay,
In the vertical case, I think you see it better if you throw it vertically.
thank you.
I have a question on the motivation of the work. So for stents. So in stent deployment, many times we're interested just on the final position of the stent and how well it fits within the artery, and transient phenomena many times it's disregarded. So I was wondering the interest also if you have checked or you are planning to check how the accuracy of this final position changes depending on whether or not you are preserving energy with your time integrator.
No, this I didn't. No, we didn't do that. No. The key feature here was just to keep to be consistent with the energy dissipation in the case of friction, in the case of viscosity, and to conserve energy numerically in the case without friction and without viscosity. But we didn't go to that.
But application-wise, do you know? Is there any niche application in stent deployment where a time energy
This is an excellent question. It's not the first time that I get this. You want to know to which extent energy conservation is important for this application?
Yes.
Well, yeah. The key thing is that you want to have a physically coherent, consistent model. So if you have energy conservation without friction and without viscosity, it's better than
Yeah, of course.
But I fully understand.
It is.
It would be nice to dig into this aspects, but for now we didn't have the opportunity to do that.
One question: these persistency conditions that you have, you enforce them, or like, or is the algorithm itself ensures that the
You impose it's already in the continuous model. If you see the slide here, this is part of the continuous model already.
Okay.
Not even this is part of the continuous model. It's included at the continuous level. If you perform the integral, etc., you see that at the continuous level you have energy conservation.
Okay. More questions from the people from Zoom? Text? Maybe I don't know. If there's any questions? It's not because I already asked. Well, then thank you again, Francesco.